Good day to Dr. Lim and Lee, and we are from Group 3. We're going to present the computational modeling in biomedical engineering. This is our group member, CHEAH, KANG, TIONG, YING, TIONG. This is our table on content, which includes the introduction, model settings, discussion, and conclusion. I'll be introduced on this study. For overview, muscle contracts, generating movement through shortening and creating tensions. The key components are series elastic element, which including tendons, aponeurosis, and contractile element, including sarcomeres with actin and myosin. Sarcomeres from nerve recruits bundles into muscle fibers. Myosin heads creates cross bridges with ATP binding sites on actin filament. In biomechanics, comprehensive models are crucial for understanding muscle behavior. Archibald, Vivian, Hughes, 1938 models proceed to elements we can see from the left beagle. MATLAB simulation based on Hughes models are conducted to gain insights into muscle responses under various conditions, emphasizing isometric painless and sudden steps length changes. And the objective of the study is to illustrate muscle behavior during prolonged contraction, isometric containers, and understanding the interaction between contractile and elastic muscle components. Second, to investigate muscle response to abrupt length changes for adaptability and resilience understanding with implications for injury prevention and rehabilitation. Lastly, to validate the effectiveness of pure muscle model in replicating known muscle behavior.
I'm Yishin, and I will continue with the model settings and model results. As stated in Hughes' model, the fundamental components of muscle as comprising two distinct elements: the contractile force-producing element CE, representing the muscle fibers, passive series elements SE, representing the elastic tendons connected to the muscle. So there are some formulas that this model obeys to. Firstly, the total muscle will be the summation length of CE and length of SE, assuming that SE has spring properties. The shortening of LCE, which is length CE, will result in the lengthening of the LSE. Secondly, force generated by contracting CE equals to the stretching force exerted by the lengthening SE, where it is here represented by the unknown P. Since SE has spring properties, it is actually obeyed to Hooke's law, where the force equals to the spring constant multiplied the change in length. It is here represented as force P equals to spring constant alpha times the difference between the length SE and the initial length SE before the contraction. Also, we have the rate of change of total muscle length and the rate of change of P as shown in this slide. The results are then constructed using MATLAB by given modern parameters for basic stretch muscle. A function file is created that accepts length and time input, computes LSE, LCE, force P as output, with inserting the parameters, initializing the arrays, creating general solver, and adding the noise. Then, the MATLAB code for first case isometric contraction has been constructed by remain the total muscle length L at 1 from 0 to 5 seconds. An output graph has been plotted. The MATLAB code for step length change also constructed by reducing the total muscle length L from 1 to 0.95 from 0 to 5 seconds, and also an output graph has been plotted.
This study applied Hughes' muscle model and MATLAB simulations to delve into muscle behavior with a specific focus on isometric tenderness and step length change. Our findings, in close alignment with theoretical expectations and existing research, provided comprehensive insights into critical aspects of muscle physiology. In the first case, the isometric tenderness simulation, built dynamic observations. The initial pre-stretch led to an increase in the series elastic component LSE from 0.3 to 0.4 units, followed by the stabilization of contractile element LCE at 0.6 units. This stabilization indicated that the changes in the total muscle length L predominantly stemmed from adjustments in LCE. As the simulation progressed, LCE remained constant at 0.6 units, indicating an isometric contraction where the muscle generated force without undergoing length changes. The steady-state force oscillation within a narrow range and constant total muscle length of 1 unit during contraction highlighted the precision of muscle force output. The force graph plateauing at around 140 mN further underscored the muscle's capability for sustained force production without substantial length changes, a crucial aspect during tendonic contractions. In the second case, focusing on the step length change, the simulation underscored the muscle's remarkable adaptability to sudden alterations in length. The output graph revealed a rapid decrease in LSE from approximately 0.4 to 0.35 units at 2 seconds, indicating the swift release of stored elastic energy within the muscle. Simultaneously, a decrease in LCE suggested active muscle fibers were shortening to generate force in response to the step change. The sharp decrease in total muscle length L at the point of step change reflected a combined response of both LSE and LCE. Prior to the step change, the constant total muscle length at 1 unit implied pre-stretching or loading, a common preparatory mechanism in muscles. The graph exhibited a substantial force peak, likely exceeding 150 mN, representing the immediate stretch response to the abrupt length change. Subsequently, the force plateaued around 144 mN, indicating the muscle's adaptation to the new length and reaching a new equilibrium. Our research using MATLAB simulations and Hughes muscle model offered important new understandings of how muscles behave during isometric tenderness and step length changes. The muscle's ability to sustain a constant force output without length variations was demonstrated by the isometric tenderness simulation, which is consistent with accepted theories of muscle physiology. The simulation of step length variations highlighted the muscle's dynamic sensitivity to abrupt changes in length and showed how quickly it can adjust to outside pressures.